So a quantum state is a density operator, and in fact, I'll give you the following result. Any normalized density operator can be expressed as a convex combination of pure states, which, as you know, are rank 1 projectors. Is there a question? Yes? Okay, a convex combination is a probabilistic combination. Is a linear combination where the coefficients add to 1. Maybe I should say a convex combination is a linear combination that's a probabilistic mixture. Yes?
Is there a good reason why a probabilistic mixture is called convex as opposed to, say,
Oh, well, convexity is the term that's generally used for, so a convex set is a set of elements where if you take any two elements and combine them probabilistically, so I have element alpha 1, and I take that with probability p1, and I have element alpha 2, and I take that with probability p2, then the linear combination p1 alpha 1 plus p2 alpha 2 should be an element of that set still. So a set is convex if it has that property, that when you take mixtures of its elements, you still get an element. It's closed under. Convex set is a set that's closed under convex combination. So this is, I guess you're thinking of like a function that's either convex or concave.
is there any reason why?
What's the origin of the term convex? I don't know. I wish I did. Is that what you're going to say? Why it's called convex?
Yeah, I was just wondering why setting that definition just makes it easier for me to understand. I don't know why.
You mean the word convex, or the why say convex combination instead of probabilistic mixture?
Yeah, why put convexity together with probabilistic mixture? Why convexity together with the definition of convex setting? It's not really.
All right, so the terminology, you're just wondering where does the terminology come from, right? Yeah, that throws me off too. But I don't know the origin of this term, so unfortunately I can't answer that question. But let me just, I'll just make this claim and you can hopefully accept it on faith. But you'll read lots of papers that use the expression convex combination, so it's good that you know what it means. This is the standard terminology. It's not some kind of idiosyncratic terminology that I'm throwing at you. Where do I want to go with this? Right, so what this means is that I can always find a decomposition of the form where PLs add to 1. And of course, we recognize these rank 1 projectors as pure states. And so I gave you the example yesterday of how one can take two states, prepare them by flipping a coin with different probabilities, and then you get a density operator out. And now I'm telling you the converse, which is that given any density operator, you can always find such a decomposition where you can prepare state phi 1, probability p1, and so on, and construct that density operator. In fact, there always exists for any, now, what's the difference between a mixed state and a pure state? Well, a mixed state is a density operator where this decomposition is non-trivial. So there's more than one element, PL, that's non-zero. There's more than one non-zero PL. A pure state is one for which this decomposition is trivial, meaning there's only one term in it. For any mixed state, who can give me a mathematical condition that tells you a state is mixed? Yes, precisely. For any mixed state, rho, i.e. trace of rho squared is less than 1, there exists an infinite set of such decompositions. So the question that was posed to me, sorry, that was just a little bit of background and context. The question that was posed is, what's the difference between a mixture and a coherent superposition? So a coherent superposition of the state psi would be of the form alpha 1 psi 1 plus beta plus alpha 2 psi 2. Let's assume for simplicity that psi 1 and psi 2 are orthogonal states. For example, they could be two states drawn from the same basis, same orthonormal basis. And this should look familiar to you. And now we know some things about alpha 1 and alpha 2. What do we know that alpha 1 and alpha 2 have to satisfy? Normalization, that's right. So that's going to say, so by normalization, we know that alpha 1 squared plus alpha 2 squared is equal to 1. So that is a coherent superposition, whereas a mixture would be expressed as P1 psi 1 psi 1 plus P2 psi 2 psi 2. So we're taking the associated density operator constructed from psi, and we're writing it as an outer product, which is this projector. And we're taking that pure state with probability P1, and we're adding in convexly this other state with probability P2. Now, to really compare these two states, we should write down our coherent superposition in the same formalism in which we're writing down our mixed state, which means we want to write down a density operator for the coherent superposition. So using psi, we find the associated density operator, associated pure state density operator. We'll call it sigma. So sigma is just equal to, I expect almost all of you should know this. How do I construct sigma from psi? Outer product. And now what we're going to do is expand it out. So we substitute our vector in here, and into this piece we substitute the dual vector. So what does that mean? That means we take alpha 1 psi 1 plus alpha 2 psi 2, and then we take the outer product. Here, I'll make an intentional mistake. Okay, what mistake have I made? Right. So when we take the dual vector, we take the complex conjugate. I'm sorry that I use both overbars and asterisks to denote complex conjugation. So bear with that redundancy of notation throughout the course. And then we just write it out. So then sigma is equal to alpha 1 squared psi 1 plus alpha 2 squared psi 2 plus alpha 1 alpha 2 bar psi 1 psi 2 plus alpha 2 alpha 1 bar psi 2 psi 1. Okay, so we've written down formally the coherent superposition, which is a pure state expressed as a density operator, and the mixture of these two states. Now, if it happens to be, now here's a conceptual question. Suppose I tell you, I give you a box with a system in it, say a two-level system like a spin half particle, and I say, well, either I put in this box, I've prepared a state via this procedure, or I've prepared the system via this procedure. I created the coherent superposition of the two. How would you test to determine which state you were given? So I guess that's going to be a loaded question unless we introduce some terminology. Let's think about, okay, at these, how many of you have seen spin half particles written out? Sorry, how many of you have not seen the spin half formalism? Excellent. So you all know what Pauli operators are. X, Y, Z, perfect. Okay, then let's think of psi 1 as the sigma z up eigenstate. So to answer my question, let's suppose that sigma z acting on psi 1 is equal to h bar over 2. Oh, so sorry, that's sz. Is equal to plus 1 psi 1, and let's suppose that sigma z acting on psi 2 is equal to minus 1 times psi 2. This is supposed to be a 1 here. So now we've identified psi 1 and psi 2 as the eigenstates of sigma z. What would you need to measure to just, let's further suppose that it happens, and let's suppose that P1 happens to be equal to alpha 1 squared. How would you distinguish these two states? I finally get to that question. Yes, Miriam?
If you measure along x or along y, you'll get different results depending on which circumstance you have. So if you have the coherent superposition, you'll actually end up with almost all of them coming out one way.
Right.
And if they're mixed, they'll be 50-50.
Exactly. So if we measure sigma z, we're not going to distinguish these two states. So if you have a state that's either a mixture or a coherent superposition of the eigenstates of sigma z, measuring sigma z won't help you distinguish that, because if I measure sigma z, then the probability of getting the up state is just equal to alpha 1 squared, or equal to P1 for these two states. So this is for sigma, and this is for rho. We've assumed that P1 happens to be equal to alpha 1 squared, so we're not going to be able to tell. Similarly for the probability of down, which is just 1 minus that. So what you need to do is measure in an axis orthogonal to sigma z. Sorry, not orthogonal. You need a measurement which doesn't share eigenstates with sigma z. So sigma x or sigma y, or any actually linear combination of sigma x and sigma y, would reveal these coherences. So one way to do that is the following. We could take, actually, you know what? I think I'll leave this as an exercise. Show that the probability of finding +1 along sigma x is different for rho and sigma. And to make things simple, let's make this simple for you. Let's let alpha 1 equal alpha 2 equal 1 over square 2. So now when I say the probability of +1 along sigma x, what does that mean? Well, the sigma x eigenstates, so the plus x eigenstate, it just says eigenvalue +1, and plus x is going to be equal to 1 over square root of 2 psi 1 plus psi 2. So I'll use the Born rule. So what's the measurement operator you're going to use for this? You want to calculate the probability of +1 along sigma x. You use Born's rule, so it's going to be the trace of rho against the measurement operator. You just have to be careful. Okay, so when you answer this question, bear in mind the following distinction. Yeah, that's right. The projection operator. So this is actually another remark I wanted to make. Let's take sigma z as an example. In many introductory courses to quantum mechanics, you're taught that measurements are given by Hermitian operators, where the expectation of, say, sigma z is equal to the trace of rho against sigma z. But now, in postulate 2, in which I introduced the spectral decomposition of the observable, O, which is in this case sigma z, we said, well, we know that sigma z can be written as the +1 eigenvalue times the +1 eigenstate plus the -1 eigenvalue. So this is the spectral decomposition of sigma z, where, of course, I guess my notation is obvious from there. So now the expectation of sigma z in this state is going to be equal to +1 sigma z plus 1 plus -1 sigma z minus 1, where I've used the cyclic property of the trace. So bear in mind that the trace, where I've used the fact that the trace of something like phi A is just equal to phi A phi.
So what is your density matrix?
Oh, this is just an this is just a general result. If I have some projector, whether it's These are just arbitrary linear operators now.
In the previous slide, did you go over?
Oh, did I make a mistake here? Oh, yeah. What did I do wrong there? Oh. This is rho. This is minus. Which is actually not really what I wanted to show you. What I wanted to show you instead was, thanks for catching that. Let me just fix this. Here, for simplicity, let's let rho equal phi phi. So rho is some pure state, which in the problem I've given you, rho won't necessarily be a pure state, but I just want to clarify the meaning of the expectation value of an operator versus the probabilities. So in this case, we have phi plus 1 plus 1 phi minus phi minus 1 phi. So now what you should do is recognize these two pieces. So let me just write over here. This is equal to, let me just put it this way. From postulate 2, we know that phi plus 1 phi is equal to the probability of outcome plus 1 given state phi, or given state rho, and phi minus 1, wait, this really bounced, minus 1 is equal to the probability of outcome minus 1 given preparation rho. So what we have here is then the expectation of sigma z is equal to the probability of the plus 1 outcome times lambda 1 plus the probability of the minus 1 outcome times lambda minus 1, where lambda 1 is equal to plus 1, and lambda minus 1 is equal to minus 1. So what I'm trying to show you is this. If I do an experiment, so in general, if I have for some observable O, which is equal to a sum over L, lambda L times projectors L. This is my spectral decomposition of the observable. And I have some preparation rho. And then this is my, remember I said that the eigenvalues are essentially labels for the outcomes. So you're going to get some dispersion of outcomes under measurement. So these are the different L values. And I'm going to have the probability of outcome L. I'll get some probability distribution. And each of these, this is equal to, each of these are each of the probability of L's. The point is that the expectation value of the operator is the mean of those outcomes. It's the weighted mean. So the point is, this is a very elementary point, so it's probably familiar to most of you. The key point is that the expectation value of A is equal to the weighted average of the outcomes. So each outcome L provides a weighting factor through lambda L, which is its eigenvalue. So we're adding up the probability of outcome L times the eigenvalue associated with L, plus the probability of the next L value times the eigenvalue associated with L. So the point of this is to show you that the primitive quantities, the really fundamentally quantum objects that we're dealing with, are the projectors in the spectral decomposition of the operator. And once I know the probability of getting this outcome, and if I collect that information in this kind of histogram, then something like the expectation of sigma x is a derived quantity. It's not a fundamental quantity. It's not something that exists in the lab. It's an average over an ensemble of measurements. So an expectation value, an expectation of a Hermitian operator that is not just a projector is in general a derived average over outcomes. I mean, I think there was a kind of a conceptual confusion for many scientists, in part because prior to the last few decades, we didn't really have the technological capability to do measurements on individual systems and collect this kind of data. I mean, in some settings you could, but in many settings one could only directly, like for example in NMR, one gets this kind of an average from the experiment directly and one never has access to this underlying information. But when you're doing experiments on individual systems, then you do have access to this underlying information. And then once you collect this data, you can later on, now look, think about this. Consider two observables, A and B, which have different spectral decompositions but share the same eigenbasis. Yes?
I thought that I have two questions about something that happened over there.
That's okay, we can all see it still.
Okay, I just didn't want to interrupt.
Go ahead.
Okay. One is, I just wanted to clarify a sentence that I thought I heard when you asked how would we distinguish between the system that's prepared in the state rho and a system that's prepared in the state sigma. I thought you said that we should measure an observable whose eigenstates are not linear combinations, or whose eigenstates are linear combinations of the eigenstates of, in this case, we said sigma z. In particular, is that we need to measure an observable whose eigenstates are non-trivial linear combinations of eigenstates of sigma z that correspond to different eigenvalues of sigma z.
The eigenvalues don't matter. This maybe is the answer to your question. So yes, you do need to, if you have a coherence between, suppose you have an atom and you have a ground state and an excited state. And you don't know if this atom was prepared in some thermal mixture of the eigenstate and the ground state, or if it's in a coherent superposition of the thermal state and the ground state. Okay, so that's the question. You don't know, so how would you do it? Well, if you're a measurement operator, when you write down its spectral decomposition, if its eigenbasis is the same as the energy spectrum of the atom, so if your observables, the eigenbasis of your observable is the eigenbasis of the atom, then you won't be able to tell, you won't be able to distinguish the coherent superposition from the mixture. in order to distinguish whether two states are coherent or mixed, assuming that the probabilities are the same for the ground state and the excited state, then you have to measure an observable which has eigenstates which are linear combinations of those states of interest that you're trying to distinguish whether they're coherent or not.
An observable which that doesn't commute with yours.
Yeah, it would have to not commute, for example. And that's probably a better way to put it, in fact. They have to not commute.
And also, so it seemed that you were making some pretty quick choices about which coefficients, for example, to use in order to simplify the problem and so on.
Yeah.
And so I can see how in general it's a good idea to try to measure an observable that doesn't commute with the first observable in order to distinguish between these two types of states. So it's a strategy that I know is around, but I personally need to go through the calculations in order to check every single time that given these weights, one observation would distinguish between the two states and another would not. How do you look at this and just see that in this case, or if you have these two types of states, the coherent superposition and the non-trivial density matrix, how can you just look at it and see that measuring in the sigma x basis would work in this case?
Because sigma x doesn't commute with sigma z.
Okay, so that just is a general,
Which is, as you
regardless of the weight.
Yeah, so you have to measure a non-commuting observable to detect a coherence with respect to some basis. So, okay, I think that I'm wondering if this is maybe too elementary for you guys. Is it? Is this too elementary? No? Okay. All right, good. So I just wanted to point out that if I have an observable, so just a remark, given two measurements, A, which is equal to sum over lambda A. Sum here, let's do it like this. Sum over L, lambda L, and another observable B over K, lambda K. I'm going to do this. Let me do it this way. AL, AK, AK. So what I'm trying to get at here is the fact that A and B share common eigenstates.
Do you want to use a different lambda symbol for the second?
Let me just do it this way. Let me call these, I need a Greek letter. Mu? Mu, all right, perfect. Mu K, let me call these BK, BK. All right, now let's suppose that it happens to be that the set lambda L is not the same as the set mu K. But let's suppose that they share common eigenstates. Let's suppose that AL BK is equal to delta LK. All right, so A and B are two observables that share the same eigenstates, but they have different eigenvalues. My point is this, is that you only need one experimental arrangement to measure both of these observables. In fact, all you want to do is really, so what's important here is that you only need to measure, you only need one measurement arrangement, measurement scheme. To determine the expectation of A and the expectation of B simultaneously. And the point is, because all you care about are the probability of outcome L, which is equal to the trace of rho AL And now remember, the ALs are the same as the BKs. And so that means once you've collected this data, which is this data here, then you can go on and 5 days later, you can say, OK, well, if I know the expectation of A, then I just weight each of these probabilities by the associated eigenvalue. So the expectation of A is equal to the weighted sum over L, lambda L, probability of L. And the expectation of B is equal to sum over L, mu L, probability of L. So the point is, this is your quantum data. This is the data. And these eigenvalues are just labels that you use later on to compute things like the average value of A and the average value of B. So I just want you to think about this as kind of a classical average over your quantum probabilities. That's the key point. I guess I'm driving home. Perhaps too pedantically. OK. Good. So that was some comments I wanted to make to clarify the postulates 1 and 2. And if there are any further questions, I'll take them now. Otherwise, I'll move on to postulate 3, which concerns dynamics. Debra.
So the convex decomposition of the density operator is over projectors which necessarily are not orthogonal.
Yes. It's probably possible to write down decompositions which involve non-orthogonal projectors. In fact, OK, I know it's possible to write down decomp, but generally speaking, for ease of calculation, one chooses an orthonormal basis for many reasons. It's good to work in orthonormal bases.
The infinite set is related to the fact that
Yeah, so an infinite set of decomposition in terms of
non-orthogonal.
in terms of orthonormal bases, in terms of distinct orthonormal bases. So generally speaking, the idea is this. You have some set of pure states. So the boundary here is pure states. And then this is a convex set, because if I take some density operator rho, so this is density operators. Density operators on some Hilbert space H, which is sometimes denoted D of H. And then this is some mixed state. And the idea is that I can decompose it as a convex combination of these two pure states, or I can decompose it as a convex combination of these two pure states. These are so these are orthonormal. And the idea is there's an infinite set of such decompositions. Which is, this is distinct from classical probability theory. Because in classical probability theory, suppose I have a probability set, P1 plus P2. So this is now, here, let me write some words down. Contrast this with classical probability. So if classical probability, suppose I have a 3-outcome event, or 3 outcome events. Then I have probabilities. My probability set is equal to P1, P2, and P3, where, of course, each PL is greater than or equal to 0, and sum over L from 1 to 3 of PL is equal to 1. This defines a simplex, a probability simplex, which I can write in terms of Cartesian components. This is the P1 axis. This is the P2 axis. This is the P3 axis. The maximum value of each of these is 1. And so this triangle which is symmetrical, which is in this positive quadrant, P1, P2, P3. Can everyone see this geometry? So this surface here, this triangular surface is called the simplex. I think it's called the 3 simplex. Which I don't know if it's, obviously there's only 2 independent parameters because they sum to 1, so I don't remember if it's called a 2 simplex or a 3 simplex, but whatever the notation is, this is the simplex associated with 3 outcomes. And if I take any classical mixed state, which means that I don't know for certainty if I'm going to get outcome 1, 2, or 3, so I'm somewhere on this surface, there is a unique decomposition in terms of the pure states. So for any probability vector P, for any P, and notice that this surface is a convex set as well, because every element within it can be written as a convex combination of these 3 outcomes, where the coefficients are P1 and P2 and P3. For any P in this simplex, there is a unique decomposition in terms of the pure states, which are these extreme points of this convex set. And these extreme points are usually called in classical probability theory pure states. I find this terminology misleading for interpretational reasons, which we won't get into. But so I tend to avoid the use of pure states when I'm talking about probabilities, but that is a common terminology. Whereas in this case, we have an infinite, as noted above, we have an infinite number of such decompositions of a mixed quantum state. So the fact that one has this discrepancy, that mixed quantum states can be written down in very many different ways in terms of the quantum pure states, but mixed classical probabilities have a unique decomposition in terms of the pure states. This discrepancy is called the ambiguity of mixtures in quantum mechanics. So the non-uniqueness of in the decomposition of mixed quantum states is called at the beginning here. Okay, any other questions before we move on to postulate 3? Yes.
I'm still confused because you said any normalized density operator can be expressed as a combination of pure states. But then, so what's with the coherent superposition because it's not a pure combination?
Yeah, so the coherent superposition written above there is not, oh, that's not the sigma here.
Yeah.
So one thing you can do is you could take trace of sigma squared. And what you would find is that that's equal to 1, because sigma is a pure state. So the linear combination there of psi, that's not a probabilistic decomposition. That's just a linear combination. Is that what the source of the?
Probably.
So yeah.
So if we express the density operator of a pure state, then there's only one term.
Right.
In that sum.
So for example, maybe this is a more directed answer to your question. Given sigma as defined above, which is a pure state, Remember, there's three equivalent ways to check that sigma squared is pure. This is one of them. Or equally, because of the fact that sigma is actually equal to psi psi, then it admits a unique decomposition in terms of projectors. So the point is, then sigma equal to psi psi is the unique decomposition, and here's the key point, in terms of projectors. So if I run to talk about the vector psi, then I can write it as a linear combination in lots of different bases. Right? Any state psi can be written as a linear combination in any orthonormal basis I choose. But when I look at the associated density operator, sigma, and I want to decompose that in terms of other quantum density operators, in particular rank 1 projectors, then there's a unique decomposition because it's pure. When it's mixed, there is a non-unique decomposition, and it's infinitely non-unique, always. So as soon as you basically there's either one decomposition or there's an infinite number. There's nothing in between. That's the point. And if there's only one, then it's pure. Otherwise, it's infinite. OK, good. Thank you for those questions. I'm sure that helps a lot of people sort through this. OK, so I called them axioms before, so I'll continue calling them axioms. Although in the notes, they're called postulates. So axiom 3 concerns the dynamics. I'll try and pick up the pace a little. So let me just power through these definitions and remarks, and then we'll have a little discussion about things that need further clarification. So the dynamical evolution, which just means the time evolution of a quantum system, is prescribed by an operator U that satisfies. Oh, I didn't get to the second question that I was asked yesterday, so we'll have to remember to come back to that. Let me just add this from T0 to T. Sorry, it's kind of obvious from context, but really I should have put that in the definition in the notes as well. Where H is the Hamiltonian, which is the energy function. And we constrain the operator U so that if T0 is equal to T, so generally speaking, I'm assuming here that, not sure if I'm assuming it yet. But when T0 is equal to T, then we demand that, I don't know if you guys can read this here. This is U of T0. T0 is equal to identity. So if no time has elapsed, then the evolution operator must be identity. So this is kind of a funny version of the Schrodinger equation. Oh, crunched that. All right. So a consequence U inverse is equal to U adjoint. So how do we see that? We take d by dt of U adjoint. I'm suppressing the argument for convenience. And what's that equal to? It's equal to du by dt times U adjoint plus U times du adjoint by dt. Now we know what del u by del t is. It's just we substitute the equation in postulate 3. So then you get this is equal to, what do I have? I have minus IH bar in the denominator. And then what is that? HU on the right there. So I have HU times U dagger plus U. Now, how do I find du dagger by dt? Well, I just take the adjoint of this equation. That makes this minus IH bar. And then I get an adjoint here. The adjoint swaps the order of U and H. And I get H adjoint. Well, U dagger, H adjoint, H dagger. H dagger is equal to H because H is Hermitian. So then we have plus IH bar of U dagger H. Something went wrong here. Something went wrong. What went wrong?
In the first term, there should be a plus in the denominator. In the second term, there should be a minus. When you take it up, you get a minus and then a plus.
What?
Yeah.
Here, let me do it this way. I'm hoping this fixes my problem. Now, du dagger by dt is going to be U dagger H. And that's plus IH bar. And then you get U dagger HU. Everyone okay with this?
First term, you get HU. Now you get HU.
Oh, thank you. All right, so clearly this is equal to 0. So we've determined that the partial with respect to t of U dagger U is equal to 0. But we also know that U dagger at the initial condition is identity, also for U. Which means that the initial condition for this differential equation is identity and has no time evolution, therefore it's identity for all time. Hence, U dagger U is equal to identity for all t. Yes?
The sign should be the other way around with the denominator.
Oh, thank you. So therefore, we've deduced that U dagger is equal to U inverse. So we know that this evolution operator is equal to a unitary operator. Okay, so now what we do is we can, once we have U, then we have the time evolution in the Schrodinger picture is given over here. So generally in the Schrodinger picture, we'll suppress the subscript. So here, rho s of t is just equal to rho of t. So here, notationally, I should probably do this. This is rho at time t0, and this is rho at time t. So then we have, given some observable A, the expectation of A as a function of time is equal to the trace of U t comma t0 rho at t0 U dagger t comma t0 times A. Where this piece is just rho at time t. So if A is a time-independent observable, which is certainly the simple and common case, then the entire time evolution of the system is carried by the state operator. And in the Heisenberg picture, which I assume you guys have all seen before, one puts the dynamical time dependence on the observable. So here we add a subscript to the observable to remind ourselves that we're in the Heisenberg picture. And then what happens is the order of the unitary swishes. So here we have and then I guess it's a matter of taste if you I guess we can also have some additional time dependence here. All right, so this is where you kind of need a quiet moment to yourself to sort through this because it can get confusing. But here, I've added a t here for what reason? For generality. So what I'm doing is I'm allowing the observable to be time dependent. So now, in the Heisenberg picture, you have two sources of time dependence. You can have an intrinsic time dependence because what you're measuring is a time-dependent quantity, and you have a dynamical time dependence, which is from the time dependence acquired through the evolution through the Hamiltonian.
So on the right-hand side, in the AH, that's also in the Heisenberg picture?
Yeah.
And the argument is T naught, T naught?
Yeah.
Looks like A sub H of C is invariant under transformation values.
It's not invariant. Oh, I see. There's right. So notationally, it's kind of inconsistent then. So what's a good notation for this? Let me. You know, I don't know the right way to notationally distinguish this, but I agree this is somehow inconsistent. But let me give you an example, and then suppose your observable is this. Suppose your observable is suppose your observable, and this is what actually happens in things like NMR. Your observable might be, it's called the observable A, equal to sigma x times cosine omega t. So what you're actually measuring depends on the time at which you measure it. So in some sense, we can add a parenthetical dependence on t here because there's a t dependence. So we think of the Schrodinger operator. It depends on time because of this factor. But now in the Heisenberg picture, maybe that's the way to do it. Maybe I can just put an S here. Maybe that would solve the problem. We have a time dependence due to, let me set t naught equal to 0. Yeah, so that's the answer. OK, perfect. I think that's the answer. So you get an additional time dependence. So here the t here kind of represents two different sources of time dependence. Let me give this to you tentatively and write down the associated differential equation, and we'll make sure everything's self-consistent at that point. So this is commonly written in terms of a differential form. dH by dt is equal to 1 over IH bar, the commutator of AH of t with HH of t plus, okay, perfect, DAS by dt sub h. So let's unpack this equation. So first of all, I've written the Hamiltonian in the Heisenberg picture. If the Hamiltonian is time independent, then this means nothing. But the Hamiltonian may be time independent, in which case one has this relationship applies to the Hamiltonian itself. And what does this mean? So this is some observable, and we're writing it in the Heisenberg picture. So this is equal to U dagger of t So now what we can do is we can take derivatives of this and figure out what we need here to be consistent with that. So these are should be two equivalent statements of the dynamics. So let's make sure they're equivalent. So let me call this 1, and let's differentiate 1. And what we get is dH of t by dt is equal to du dagger by dt times the remainder of the expression plus U dagger dH by dt U plus U dagger AH du by dt. And now we substitute the Schrodinger equation, which I've written down somewhere, or I guess Oh, I erased the wrong board. Okay. All right, I have to do this in my head. So let's see. That's minus IH bar, so it'll be. So if you guys could do this in parallel, make sure I don't make any sign mistakes, I'd appreciate it. This is going to be U of U dagger H that doesn't look good. It's not what I want. What? Freaking mess. Okay, this is really surprising me. This shouldn't look like that, but oh, okay. Well, maybe it'll all come together at the end. Oh, I think okay. I see what's going to happen. It's fine. U dagger dH by dt U plus U dagger AH, and now du by dt is going to be plus IH bar over H U of t. And now what we probably have to do here is insert a resolution of the identity, which is U dagger here and here. And then right over here, we get U dagger HU, which is equal to H in the Heisenberg picture. U dagger AH is going to be AH of T over minus IH bar plus this is dAH by dt. Okay, this is where we're figuring out our error. Perfect. Plus here we have AH of t times HH over plus IH bar. And so now if we compare, so this is going to be the commutator here. And then this term doesn't match, which means we should have had an S there, which means this should be an S. So that's the fix. OK, so yes, thank you for picking up on that. So we want to put an S here and understand that if this has time dependence, it's the intrinsic time dependence of this form. And then we have an additional time dependence in the Heisenberg picture due to both the intrinsic time dependence and the unitary. And then if we replace that here, then we have this is AS, This is AS. This is AS. This is AS. This is AS. And our substitutions follow through. Where this AS became an AH because we sandwiched it between the time evolution operators. Okay, so that's our consistency. So good. So that's right. Okay, so we'll discuss some further aspects of postulate 3, I guess, next class since we've wrapped up. Are there any questions before we wrap up for the day? Yeah.
For the time independent operator, does it mean that the observable is also, the expectation value is also time independent?
Here?
Yes. So if the A dagger, A is a time independent operator, and on the right hand side, the trace, then you can interchange the.
So yeah, so the expectation value is going to be time dependent. So think of this as a quantity, as a real valued variable.
Yeah.
That real valued variable will be time dependent. And it can have two types of time dependence. It can have a time dependence from an intrinsic time dependence of this type, which has nothing to do with the unitary dynamics. And it can have a time dependence from the unitary dynamics.
Back here, if there's intrinsic, there's no intrinsic time dependence, then just the trace of that's the unitary evolution of the density matrix will give the same trace.
So
I mean, you can interchange those operators inside the trace for that same value.
yeah, you can bring this one over here, which is what I did here.
But can you interchange the unitary as well?
Oh, you can't change them. They don't commute. Operators don't commute, so you're not allowed to change their order.
The traces.
Inside, so there's this, okay, what you're thinking about probably is the cyclic property of the trace. So the trace of A, BC is equal to the trace of BCA is equal to the trace of CAB, but is not equal to the trace of BAC. So I just changed these two. That operation is not allowed for operators unless they commute. Okay, good. Okay, good. We'll wrap up postulate 3 next lecture. Thank you for your attention.